Hi and welcome back to my YouTube channel, and today I'm going to be looking at stationary points on a graph, and more specifically how we can use differentiation to first work out exactly where a graph is stationary for any given graph, but also to look at the nature of those stationary points, and again how we can use differentiation to work out whether a point is a minimum, a maximum, or what is known as a point of inflection. So to start off with, let's look at the graph y equals x cubed minus 7x minus 6. If we look at the graph, we can see that there are two stationary points, a point here and a point here. And say I want to work out what the coordinates are of those stationary points. I need to work out the x value of that point, of those points, and also the y values of those points. So how can I figure out the first of all, the x coordinates of these stationary points? Well, say I was to draw tangents at each and every point of this graph, you can see that the graph is stationary if and only if dy by dx is equal to 0. So we have the definition here. A point is stationary on a graph y equals f of x if and only if d by dx of f of x is equal to 0 at that point. Luckily, as this is a cubic that does not have what's known as a point of inflection, we can see that this graph has two stationary points. Since d by dx of f of x has to equal 0 at those points, what we first have to do is differentiate this function by using the power rule, but also combining these two laws of differentiation, which you can see proved in a previous video. dy by dx is equal to 3x squared minus 7. And so, as dy by dx is equal to 3x squared minus 7, dy by dx is equal to 0 if and only if 3x squared minus 0 is equal, 3x squared minus 7 is equal to 0, which is true if and only if x is equal to plus or minus the square root of 7 over 3. So we've got two solutions for x. So to work out what the y values are at those points on the graph y equals f of x, we need to plug in the values of x back into y. So when x is equal to positive 7, the square root of 7 over 3, then y is equal to, so the y value at the point x equals positive the square root of 7 over 3 is equal to minus 14 the times the square root of 21 over 9 minus 6. So as we can work out the y value by plugging this positive square root of 7 over 3 into x, at this point we can see that this stationary point has the coordinates the square root of 7 over 3 and minus 14 square root of 21 over 9 minus 6. And you can simplify this if you want and make it minus 54 minus 14 square root of 21 over 9 if you really want to, but it doesn't matter. So we know what the y value is at this point. And then we can also use that kind of logic to work out the y values when x is minus the square root of 7 over 3. 14 times the square root of 21 over 9 minus 6. So you can see that we can work out what the values are at these stationary points. We can work these values out by simply working out dy by dx, setting this to be 0, because those are the only points where the tangent line is perfectly horizontal or parallel to the x-axis. And then by rearranging, you can find at which point x the graph is stationary. If there are any points, there will be graphs that don't have any stationary points. For example, if we look at the graph y equals e to the power of x, that graph is always increasing for all values, so it has no stationary points. Well, we can use this to work out the nature of these stationary points. You can see that this point is a stationary point, but you can see that it's almost at the bottom of its area. Like locally speaking, if I was to take values from the range -1 and 3, the value at x equals positive the square root of 7 over 3 is the lowest value of the graph. It's like it is a turning point, but it's almost like it's a minimum point, and that's what it is. So this value here is known as a minimum, and to work out the nature of a local minimum point, you can see that to get to a stationary point, the derivative at that to the graph at that point has to be 0, correct? But as you can see here, the tangents to the graph at these points are all, well, let's draw them on. So that's negative, that's negative, that's negative, that's negative, and that's negative. But then it slows down and gets less and less negative to become 0. But then here, it's at 0, and then all of a sudden, after this point, the graph becomes positive. The gradient of the graph, sorry, becomes positive. You see, like, the tangents are pointing upwards now, and they get slowly and slowly and slowly become more and more upwards in this case. If the graph was negative, then went to 0 and then went negative again, then there are y values that are smaller than this y value. The graph goes lower. But if the graph goes low and then lower and then hits a point where the graph isn't going any lower, and then the graph goes up, that means that's the minimum point. So as the gradient is negative, for all the points where the gradient is negative, the graph is decreasing. Its value is decreasing. It's going down and down and down. But once it gets to a point dy by dx equals 0, and then becomes positive again, we end up with a minimum point. And the opposite is true for maximum points. So we see that here dy by dx is positive, right? Because the gradient is positive. But then we get to a point dy by dx equals 0, and then you can see here dy by dx is negative. So how can we use differentiation to actually work this out, whether the graph is a maximum or a minimum at those points without drawing the graph out? Well, as you can see here, if we find the second derivative, and to do that, I'll graph out this graph dy by dx with respect to x. We can find the gradient at any specific point of the derivative function when compared to x, where instead of my y-axis being my y-axis, it's now my dy by dx axis. And so we can find the rate of change of the derivative with respect to x. And this is denoted as d squared y by dx squared. It's the rate of change of the rate of change of the graph. And so, if d squared y by dx squared is negative, then dy by dx is decreasing in value. But if d squared y by dx squared is positive, that means dy by dx is positive, and this is basically the same as this graph. But if dy by dx is 0, the graph is stationary. Here, dy by dx is negative, here it's positive, here it's positive. It's the same logic. So if I know what the value of d squared y by dx squared is at these stationary points, then I can work out whether the graph is a minimum point or a maximum point, or even a point of inflection. So a graph is a minimum point when, well, dy by dx is 0, and, well, since at a minimum point, dy by dx goes from negative to 0 to positive, if it's going from negative to 0 to positive, that means the value of dy by dx in this range is getting more positive, right? Especially if we go to very, very small values. Because if you think of a number line, it's going from a negative value and it increases to 0 and then increases to a positive value. The derivative of the derivative would have to be positive because you go from negative to 0 to positive. And likewise, at maximum points, dy by dx is again equal to 0, but d squared y by dx squared is less than 0 because you're going from positive down to 0 down to negative at these infinitesimal points here. And if you want to look at dy by dx and compare that to x, at the point x equals positive 7 over 3 and negative 7 over the square root of 7 over 3, you can see that, well, this value is, the gradient at this point is positive, so d squared y by dx squared is positive. But then here, d squared y by dx squared is negative, right? Because it's going down, the gradient's going downwards. And you could even work this out analytically by just differentiating this graph here, by differentiating or finding the derivative of this function with respect to x. This implies that d squared y by dx squared is, by using the power rule and the laws of differentiation, this is just equal to 6x. So at this point, x equals positive the square root of 7 over 3. D squared y by dx squared is equal to 6 times the square root of 7 over 3, which is positive. But at this point, d squared y by dx squared is equal to 6 times minus 7 the square root of 7 over 3, which is less than 0. This point here is a maximum, and this point is a minimum. But I've said that here, this is a local minimum. And what I mean by that is, if I was to only look at positive values of x, then this point here would be my overall minimum. But say I had looked at the whole graph, well, there are clearly values here that go to negative infinity for very, very large negative values of x. So say as x tends to negative infinity, the y value of the graph also tends to negative infinity. So locally, so at points around this this minimum point, this is the minimum value, which is why it's called the minimum point, because the graph decreases to that point then increases. And where this might come in more useful or more prevalent is, say I've got another graph. If I look at values in this is a minimum point, right? Because dy by dx is going to be equal to 0, and if you can work it out on this graph, y equals f of x, d squared y by dx squared is going to be greater than 0. But it's also true for this point here. But we can see graphically, or we could even work this out, that the y value here is less than the y value here. So that means this is the overall minimum for all positive values of x, and say this graph didn't even go to negative infinity, just when it was asymptotic to the x-axis, this would be the global minimum for the whole graph. And the same applies with maximums. This is technically, positive infinity would technically be the global maximum for this graph. But say instead of going all the way up there, I just let this go down and plateau here, again to some other value, some finite value. This would be my global maximum, and these 2 points would be my local maximums. They're locally the biggest value of y there is at those points, but when we're looking at the whole graph, this is the biggest value of y. And this is where the notion of a second derivative can come in. And in fact, we can use this idea of a second derivative and extend this to an nth derivative, where this is the derivative of the n minus first derivative of y with respect to x. So it's the derivative of the derivative of the derivative of the derivative, and we do that n times. And finally, I should go on to what a point of inflection is. A point of inflection is, say I've got yet another graph, and I'm going to let this be the normal cubic of, well, not normal, but the cubic y equals x cubed. Now, as you can see here, if you look at dy by dx, the gradients of the tangents of this graph is positive, but then it gets smaller and smaller and smaller and goes to 0, but then becomes positive again. So here dy by dx is positive, then it goes to 0, but then again goes to dy by dx being positive. This would be a point of inflection if dy by dx was negative, then went to 0, and then became negative again. And a nice way of thinking about this is, if you get a point of inflection, that means dy by dx is equal to 0, and d squared y by dx squared is equal to 0. Because, well, if I was to find the derivative of y equals x cubed, I'd end up with dy by dx being graphed to x, giving me y equals 3x squared. And at this point, at the point x equals 0, where my initial stationary point is, this graph just touches the x-axis. It's tangent to the x-axis at that point. So when we get a point of inflection when, if we graph dy by dx to x, we get a graph which at some point is tangent to the x-axis. D cubed y by dx cubed would have to not equal 0, because if you see dy by dx and compare that to x, the derivative of the derivative, so the derivative of this graph goes from negative to 0 to positive if we compare the derivative to x. But if d cubed, that means d squared y by dx squared goes from negative to 0 to positive. The gradient itself, if we graph dy by dx to x, goes from positive to 0 to positive, which would mean the second derivative would be an increasing. If we were to write the second derivative in terms of x, or graph the second derivative, it would be an increasing function or a decreasing function. And at which point d cubed, the derivative of that graph, at the point where d squared y by dx squared would equal 0, could not be tangent, if that makes sense. Because if this was tangent as well, then let's say it was tangent. And I'll do it with red because there's red flags all over this. If d squared y by dx squared was tangent at this point here, at the same point x equals 0, then, well, that would mean d squared y by dx squared would go from positive to 0 to positive. But here we see d squared y by dx squared goes from negative to 0 to positive, or it would go from positive to 0 to negative. But if d cubed y by dx squared was equal to 0, then we'd have to go from negative to positive to negative, rather than positive to 0 to negative or negative to 0 to positive. And then we'd have a contradiction. And I know I haven't explained that particular bit quite well enough, but you can hopefully see and even hopefully test out for yourself, and maybe test it out for yourself, to see that if dy by dx was equal to 0 and d squared y by dx was equal to 0, then d cubed y by dx cubed, the third derivative, the derivative of the derivative of the derivative of f of x or of y with respect to x, could not be equal to 0. And if all three were equal to 0 at some point, then the only way that could be is if we had a completely stationary graph. If these are true and they're all equal to 0, then this implies that y is equal to 0 for all values of y. And that's why point of inflections can't have the third derivative equaling 0. But that's not an important condition, I don't think, for A-level, and I haven't really come across anywhere where it's actually been useful just yet. So this is how stationary points on a graph can be worked out, and the nature of each stationary point on a graph can be worked out from differentiation and the second derivative of a graph. And by introducing this idea of a second derivative, we can find an nth derivative, and the use of this will come in something that is known as Maclaurin series, but that's a story for another time. So please make sure to like, share and subscribe, and until next time.